Welcome back to a new video lecture, and here we discuss some problems related with this static method to determine the collapse load. In the previous lecture we already discussed some of the problems related with this propped cantilever beam, then simply supported beam, how to calculate those collapse load. Okay, so this is one of the question today. This determine the collapse load in the case of fixed beam. Point load W is acting, it is not acting actually at the center, at a distance of A from the support B and B from the support A. That's the case. So you already know that first of all you need to calculate the fixed end moment values. Okay, so that actually that value is going to be W AB square by L square, and here minus, and here W A square B by L square. Actually this is the case. So you can represent that value as this MP, plastic moment. Okay, that's represented in this way. And here, what about this value? Then you have to consider this point load is acting the free moment diagram, that is WAB by L. That is represented in this way, WCAB by L actually. Then up to this is MP, and here it is MP. So total it is going to be 2 MP, which is going to be equal to this WCAB by L. Then if you equate those values, you will get the equation. This collapse load is 2 MP multiplied L by AB. That's the case. And if the point load is acting at the center, then if you substitute those values, you will get 8 MP by L. So that's the case. WC equal to 8 MP by L. So that's the case regarding this question. And if you observe the next one, that is a propped cantilever beam is here provided with a load W, a uniformly distributed load is acting over it, and our aim is to calculate the collapse load, and the plastic moment capacity is represented as MP. So in this case, this cantilever beam, actually you need to calculate the, if it is a cantilever beam provided, then here it will be a reaction will be obviously here. So due to this reaction there is a bending moment value will be in this way, so that is represented here. So if you observe clearly, you will get this MP value. Okay, then if you observe that due to this W, actually this magnitude is going to be W multiplied by L. So the reactions will be WL by 2, and here also WL by 2, isn't it? This WL by 2 and WL by 2 will be here. So our next aim is to calculate to determine the bending moment values using those values. What about that magnitude? Okay, so in this case, for the formation of collapse mechanism, plastic hinge has to develop at a fixed end at any point in the portion AB. So that's the first statement. So actually in this case, how many number of plastic hinges are needed actually? So if you consider the number of redundant members, actually number of redundant is going to be, in this case there will be a vertical force will be here, a moment also will be here a vertical. So number of reactions it is going to be 3. Then equilibrium equation 2. So 3 minus 2, 1. Plus 1, you will get the number of hinges. So 2 hinges are needed. So 1 hinge is provided at this point, and our next aim is to provide the hinge at the other point. For finding out that hinge point, there is a statement here. Please check out this statement. The bending moment at any point should not exceed plastic moment MP. The interior hinge will be at the point of maximum bending moment. So that's a statement. So you need to calculate at which point the maximum bending moment will occur. So let us take a section over this position. Let us take a section. So if you consider a section over here. So let us take a section here. So obviously the value it is going to be, if you consider this value is mx. So mx is going to be WL by 2 multiplied by X. Okay, so it is represented as collapse load. So WC multiplied by L by 2. L by this value, actually this load value multiplied by distance. Okay. Then what about this value? This WC multiplied by X square by 2. How you got that value? Actually this magnitude is going to be W. So this distance is X, then the half the distance, that is X by 2. So that is represented as in this way, minus WC X square by 2. Then here a small value is also represented. Actually that represents this value actually. Okay, that is, if you take these similar triangles, then you will get these values, that is MP by L equal to, already we determined in the previous case, Okay, MP by L equal to this value, it is going to be, let us take that value as y, then y by x. So y equal to MP x by L. So that is written here. Okay, then to find out the maximum bending moment, we need to take the differentiative and equate to 0. So if you equate and you finally get the value of MP as this one. Okay, then the hinge will be formed at the distance x that we are actually assuming. That means the hinge point to be at the point mx. So you can equate mx equal to mp, and if you equate those equations, okay, if you equate those equations, that means if you are substituting this mp value here, the equation will become in this way. And after that you have to substitute those values. This mp value, you know, this is the value actually you got. So after that you have to substitute this mp value here, and if you substitute those mp value in this way, and you already know the mp value as this wc by 2 multiplied by L multiplied by L minus 2x. So you have to substitute those values. Then if you equate those values and finally a quadratic equations you will get. And if you take the values finally, this x equal to 0.0141 L. So at a distance of 0.014 L you will get the maximum bending moment, and if you substitute those values, the MP value, it is going to be 0.0858 WCL square, and if you rearrange those terms, the collapse load, it is going to be 11.655 MP by L square. So that's the statement. So at a distance of, the plastic hinge will be forming at a distance of 0.414 L, and the magnitude of this collapse load, it is going to be this one. So that's the case. The next one is to show that in a propped cantilever subject to a moving constant load, the worst position is at 0.4141 L from propped end, and its load carrying capacity is WC equals 5.2828 MP by L. So that's the case. So a propped cantilever beam is provided here, and a point load is moving from here, from this point to some points, and it is mentioned that at a distance of 0.414 L from this propped end, and this load carrying capacity is going to be, we need to prove actually this value, this collapse load value is going to be 5.828 MP by L. And you know that the equation we already derived in the last class, this WC equals L plus B by AB multiplied by MP, the collapse load equation we already derived. And if you rearrange those values, that is, if you substitute those, the total, let us take this total distance is L, and if you can rearrange those values, that is, substitute for A as L minus B, you can write down the equation in this way, isn't it? So that's the case. So our aim is to calculate the WC, the collapse load value, to be minimum. For that also we take the derivative values. With respect to B, we are taking the derivative. Okay, all the terms are mentioned in B. So here you can take the derivative with respect to B, and it is going to be equal to 0. And this, in this case, take the you are going to take the square. So that means actually if you open up this bracket, that is L, this B to be take outside, that is B multiplied by L minus B actually. So B square, and here also L minus B all square you will get, and take the derivative in this way. Okay, so after that again a quadratic equation you will obtain, and then if you rearrange you will get the B value as 0.414 L. So if you substitute those values in the first equation, you will get this equation. So that's the case. This collapse load value is going to be 5.828 MP by L. So that's the statement. So our aim is to prove that at a distance of this 0.414 L, this WC value is going to be 5.828 MP by L. So that's these are different cases related with this static method actually. Okay, so our next aim is to calculate this same type of problems using the kinematic method, how to determine the collapse load and plastic moment capacity likewise. So regarding those kinematic approach we will discuss in the next class. So with this we wind up today's section. Thank you.